All right, welcome to Civboot Podcast 2. Again, I'm Rhett Berg. Let's jump right into it. Hopefully the audio quality here is not too bad. I spent a good amount of time trying to get the microphone to work with my Android phone. Don't really have much of a setup right now. So, unfortunately, I'm just recording this on the phone. And we'll have to have potato quality audio. Oh well. So first I'd like to lay a little bit of groundwork from the last episode, kind of set some expectations. One of the things that I want to talk about is the time frame for Civboot. This is not really something that can be done in a few years, probably 10 years, 20 years. And part of the important thing on this, especially in this podcast, is the discussion of patents, technologies, things like that. If it takes a while, one of the nice things about patents is that they, after it's patented, after a certain amount of time, it's released to the public domain. So it's kind of a process for open sourcing hardware and processes, actually. And in this time frame that a Civboot is working in, this is fine. Some of the technologies I'm going to talk about are old, so they've already been opened. Some of them are newer, or haven't been developed yet, but if they are developed and they are patented, eventually they'd be open to the public domain. So that's kind of the time frame of the Civboot. It's unlikely that this is going to be built in less than 30 years, the first Civboot. So it's a good thing to keep that in mind when talking about this. Also, another important thing is what are the minimum requirements of the Civboot? So it has to be able to produce the foundations of civilization. That's computers, basic communication protocols, automation, that kind of thing. But for level 1 Civboot, it doesn't have to really beat computers past 1980s or so. They had operating systems, text processing, storage, communication, really basic rudimentary communication protocols, but you could bring modern standards there to bear. It doesn't require excessive hardware to be able to do communication, really. So even a Z80, which has 9,000 transistors, I mean, you compare that to modern CPUs, they have millions and millions of transistors. It could do 15 megahertz, and it could run a full operating system, and you could write code, compile for itself, etc. And actually, in a later section, I'm going to talk about. I've been really busy reading about these other efforts. There's an operating system called Collapse OS. It literally, in 5 kilobytes, boots an entire operating system and can run a fourth compiler with a text editor, everything. And it can cross-compile for other systems. So, you don't need a huge amount of hardware, a highly complex chip fabrication process in order to be able to fulfill the minimum requirements for Civboot. That's one of the expectations I want to set here. But this episode is going to be mostly about silicon purification processes. Not the chip manufacturing, but those depend on pure silicon. And this is one of the major issues with a Civboot. Achieving pure silicon, or maybe not pure silicon, maybe another medium, we'll get to there, is one of the difficulties. So why is pure silicon needed? A little bit of background, a little bit of physics, electrical engineering. I have a degree in electrical engineering, and I took a few courses on this. I don't have a master's or anything. I'm not an expert. But, so why is pure silicon needed? It's because of the physics of developing a transistor. It depends on very specific voltage drops, reductions. It depends on a pure crystal silicon with a specific amount of dopant, so a specific amount, and these are like parts per million, parts per billion of specific atoms in order to change the electrical characteristics of the silicon across certain boundaries, and that's how a transistor is made. That's a really rudimentary understanding. But a pure silicon crystal, single crystal silicon, is essential for most modern computer chips. We'll get to some alternatives in a second here. And And a little bit about the cost, the history of the cost. Silicon fabrication has been skyrocketing over the years. In 1970, the cost of building a plant was about $3 million. So that's kind of like the Z80 computer chips. I think that was a little later, 1975 or something. By 1980, it had reached 75 million. So that's 20 times or more. And it had continued rising. Oh, a lot of this stuff will be in the show notes, by the way. In the 1980s, it had continued rising. And by 85, it had risen to about 150 million. And it's now standing about $20-30 billion to build a new silicon fabrication plant. So what I thought when I was first researching this was that we needed like half a gig of RAM. We wanted like a half a gig processor speed, things like that. But on researching Collapse OS, things like that, you could actually get quite a ways with a very minimal operating system. I think more is always better. Being able to develop more sophisticated tools, visual tools, things like that are going to require larger RAM, larger processor speed. But we'll get more into the software, how the software can be simplified, I think, using things like, instead of using graphical GUI systems, using, for instance, to do CAD, computer-aided design, like creating a chair or something. You could use a programmatic method to define how the chair is made instead of have a full visual suite that requires high processing speed. So we'll get into some of those alternative design choices, which can help simplify the Civboot software and require less hardware. So we'll get into some of that later. But those are some of the ideas to keep in mind. So this is too expensive. $3 million, I mean, that's really expensive, but maybe it's achievable. You could have like a university scale Civboot that has a $3 million silicon fabrication plant, and maybe it's possible with new technology and new processes. We could make it even cheaper. But it's important before thinking like maybe we could do it to understand a little bit about how silicon is purified. So purifying silicon is done by melting sand, first of all. Just sand is mostly silicon. Silicon is the second most abundant element on Earth. Oxygen is the most abundant. So you melt sand in what's called a submerged arc furnace. No expert on this either, but it's basically, I think, some rods and ultra high current push through the sand, and it melts the silicon. The arc furnace, from what I researched, is typically manufactured via steel and refractory metals. Like that's the basin that contains the melted silicon. I saw some other references that it can actually be made of quartz. I think quartz is a purified form of silicon. It's just SiO2, silicon and oxygen bonded. And it has a higher melting point than, I think, typical sand. So you can kind of see how that might work. But it requires extremely high electric power. And it ends in what's called MgSi, metallurgical grade silicon, like, the grade of like iron or tin. They're not pure metals when they come out. They're metallurgical grade. They have a few impurities, and that's okay for the development of most metals. But for the development of computers, that's not okay. There's another method that's newer, where some researchers have managed to powderize the silicon, and we'll get into that as well. But that medical grade silicon is then powderized into smaller, like I think micrometer sized granules, and put through several chemical reactions at mostly low temperatures in order to produce polysilicon, which is pure silicon to the parts per billion kind of ratio. And that takes several chemical steps, but it seems like fairly standard chemical processes where you dissolve the silicon into acids that produces some kind of chemical. The impurities form a different chemical, and then you use distillation. So like the chemicals at certain temperatures form gases, and you pull those gases off in order to distill down to the pure silicon elements and then use other chemical processes to extract the silicon. That's the basics of how pure silicon is made. But pure silicon is not the end of the story. Computer chips don't just require pure silicon. They require a pure silicon crystal, single crystal. The way to imagine this is, imagine that the silicon is an atom, and it's bonded to another atom, and another atom, and another atom, and another atom. It's kind of like a lattice, like a box. It's like a perfect box. And that's the atom level, so there's, billions of atoms in your finger. Every single bond is another perfect box that matches perfectly with that box. That is a perfect crystal. And a computer chip requires a perfect crystal with very, very few defects. And defects can be introduced in all sorts of ways in the process, such as growing the crystal the wrong way with the wrong temperatures, having impurities, things like that. They cause the two lattices to be different, and that changes the electrical processes, the electrical properties, of the wafer, which means that your computer chip doesn't work if you have too many impurities. If you have defects in the wrong places. So how do you grow a pure crystal? There are two types, for what I saw, that are mainly used in industry currently. That's called the floating zone and the Czochralski, named FZ and CZ. FZ is primarily used for creating ultra pure silicon, but it's only 5% of the silicon that's produced in industry. It has some issues with wafer processing because the wafer's a little weaker to temperature changes. The CZ method actually introduces impurities or something, and it ends up making a stronger. The impurities introduced are somehow make the crystal stronger. I haven't 100% understood why. So a little bit about these two processes, though. The CZ method, that I'm going to butcher this name, Czochralski method, silicon's melted in a quartz crucible. So quartz, again, has a higher melting temperature than the silicon, so it doesn't melt, even though it's made out of silicon dioxide. But this is pure silicon, so only silicon, no oxygen in the the polysilicon. So it's melted in a quartz crucible. This is in like like an argon or pure nitrogen gas or something like that. And it's slowly pulled. A pure crystal is lowered into it. So a single crystal, a tiny single crystal is lowered into it and slowly pulled up. And the pulling speed, it's also rotated, and the pulling speed and rotation, as it's pulled up, the silicon solidifies and hardens and forms a pure crystal. It matches the crystal that was put in. And the pulling speed and the rotation, there's all sorts of magic, quote unquote. Like, they don't know why the specific pulling speed is necessary, but that's how they make. It slowly pulls up a cylinder of pure silicon, and it has to be adjusted because the temperature in the vat is changing constantly because you're removing silicon from it. There's temperature differentials all over the place. It's very complicated and very expensive. And then at the end of the process in the CZ method, there's some silicon left over in the crucible, this pure quartz crucible, which is quite expensive. And the silicon hardens and it actually cracks the crucible. So it's a one-time process for each crucible, which is quite a significant cost. It's actually one of the most significant costs, apparently, in growing pure silicon. And it's also a very significant cost if you think about, in a Civboot context, this would be amateurs attempting to do this. They'd be making mistakes. Well, if you make a mistake, guess what? Gotta get a new crucible. So the CZ method, from what I've seen, is not applicable to a Civboot. There's no way it could ever be used in a Civboot. It doesn't scale down. It destroys your crucible each time, so you can't try again. Because it's very expensive for each attempt. The SC method has its weaknesses, but it goes the opposite direction. Basically, you start with a pure silicon rod. It's not a single crystal, but it's a pure silicon rod. You put the single crystal on the bottom. You do some special process to heat it up and melt it to the rod, and then you slowly lower it and melt the rod above it, and the rod turns into pure silicon. And this does not destroy a crucible at the end. It has several benefits. Now, do I think a Civboot is going to be able to replicate either of these methods in anytime in the near future? Not many of them. Maybe there could be a single university or a couple universities who invest heavily into creating these kind of infrastructures to be able to grow this for a Civboot project. And that would be extremely valuable. I don't 100% know whether it's economical, whether it's possible for that to happen. But that, if it were to happen, that's probably how it would happen. It would be great if there could be more. But I don't have a lot of faith in silicon manufacturing ever reaching the public domain and ever reaching a group of like amateur volunteers, even very dedicated ones. Maybe, but unlikely. Possible in the university setting. So a Civboot, being an educational tool, could appeal to universities, and maybe through that mechanism, silicon growing could be done. Also, even after you do purify it, it has to be cut into wafers in a very precise fashion using diamond saws, because it's silicon, very, very hard material. It has to be perfectly along the lattice, and then you have to polish it perfectly. There's a whole process with that. And then you have to take this wafer and produce transistors on it. And I'm going to do that in the next section. That's a whole nother process. Now, yeah, so I had some notes here about the silicon process. Let me just scan through here. Yeah. One item, regardless of whether these processes can be understood and replicated, they're extremely complex, labor-intensive, and dangerous. It'd be very difficult for anything smaller than a university or a large company to build. That's what I said. Now, it's important to note we probably don't need large wafers because we're doing smaller scale processing. Modern industry is making wafers that are really large. It's very difficult to produce large wafers. Back in the day, they were like this big. They were like 4 inches across. Now they're like a foot across or something, foot in diameter. You don't need the large wafers. You don't probably need the purity levels. Like I said, 9,000 transistors in the Z80. Maybe we can produce a chip like that that's smaller. But even still, silicon's going to be very difficult. So this gives us 2 options: reduce the cost and complexity of silicon, or find a different process. We don't actually need to produce silicon. We just want to produce computer chips. Can we do that? Yes, maybe. You can. In fact, they've done it. Albeit for very low processor speed and mostly in research settings, but it does exist. There's something called nanomagnetic logic. Now this is like a pie in the sky sci-fi concept. They've only produced some transistors. They've not produced a full chip as far as I could tell. But basically it uses tiny nano-sized magnets that can spin according to a magnetic clock, and if you arrange them the right way, they can act as a logic gate. They're next to each other, and so their magnetic orientation affects later computations. So it creates a circuit. This is extremely beneficial because it's apparently very low power, and if the computer turns off, it can reboot in the exact state it was in. There's many benefits to it, but it's not really well demonstrated currently. And it's nanoscale stuff, so it's probably pretty difficult to implement, but it's worth paying attention to. The one that I'm most excited about for Civboot is the nanotube CPUs. So I think, theoretically, growing nanotubes is actually not all that difficult compared to manufacturing pure silicon. There's methods, various methods. I haven't researched it extensively, but growing nanotubes is possible. Could be possible outside of a university setting even, but certainly within a university setting. And a nanotube CPU is demonstrated to work at low speeds, a full CPU, running a RISC-V processor at 1 megahertz. And DARPA even did a press release that the process does not require pure silicon backing, requires only low temperature processes. And for me, it indicates that it might even scale down. You can do a smaller scale process. They've actually demonstrated that it can work using existing semiconductor fabrication processes. So that's really good news. So again, the time scale that the Civboot's operating under is very unlikely we're going to produce a full Civboot in less than 30 years. I mean, maybe with like a Z80 processor, you know, and some university support, we could use the silicon manufacturing or maybe a nanotube manufacturing to have a very low speed processor with very limited RAM and memory that could produce the circuit. The software could have the circuit design software to design new circuits, because that's one of the requirements of Civboot, is that every layer is understood and you could redesign the Civboot using only the tools in the Civboot. Now you're not going to get graphics processing with that low of processing speed, but people were designing circuits back in the day before graphics, extensive graphics existed. So it's certainly possible. But this space is definitely I think it's important to note, this space is definitely the hardest for a Civboot to meet, but it is physically possible. I do believe that given enough time, and I'm talking like 20, 30 years, 2 or 3 decades, this technology can be simplified and the cost can be reduced sufficiently that a Civboot could be built. And that, I think, gives us the greatest hope for simplifying our technology stack so it can be understood. And so people who want to learn about it can build every step. And societies that want to become technologically capable can have a place to start from. Both a place for their citizens to learn and a place to build from. Because even though Civboot is great, proprietary software, proprietary hardware, improvements that geniuses make is also great. Both can coexist together, and in fact, I think a Civboot supports the latter more than anything which currently exists. It's also worth mentioning that open hardware is starting to really take off a little more than it has until very recently. And that will be another topic that I discuss in future episodes. All right. Thank you so much for listening. Hope you enjoyed the podcast.